Well, first I want to thank everyone for coming to the talk, especially on the Eclipse Day. I wear the Eclipse T-shirt for the event. So I think I'm supposed to explain to everybody in the KITP about our program, Gapless quantum matter, and there's a correlated in front of it. So what it means and what we cover and why it's interesting. Yeah, and so on. So let me explain these words one by one. So first of all, what is matter? What is matter? Okay, so matter. Yeah. So what is matter with you actually? So matter actually we define matter in an extremely broad sense. So matter can mean matter found in nature. So for example, actually, there are some, very old materials that you can find in nature, but actually modern day techniques can find something very interesting in it. For example, there's something called a Herbert-Smithite. Actually, it's found in nature, but actually nowadays people are studying it because actually it's a candidate for something called a spin liquid, okay, which is one type of quantum gapless matter. Okay, and also we also can mean that actually, first of all, matter found in nature, and second, matter which actually are not found in nature, but actually are made in lab. Okay, matter made in lab. So the most famous example of this is like the moraine materials. So actually we know in nature we have a graphite. And then from graphite to graphene is actually a small step ahead. We just need to scotch tape, and actually we can actually make one layer of the carbon atoms and make it a graphene. And then we can twist them and actually then stack them together. And this twisting and stacking is actually not a very natural process, but nevertheless, our very talented experimentalists can do that. Okay, so we can make some matter in lab. These matters are not found in nature. So we also discussed this. And three. Okay, so now actually I'm getting even more loosely defined matter. So matter exists only in computers so far. Okay, so for example, actually we had I think 2 weeks of discussion and the focus weeks on DQCP, deconfined quantum critical point, and actually that field actually is driven by the joint forces of the theorists and numerical experts, and of course those models people simulate in those models simulate in computers. Actually, I would say that it's difficult to find a realistic realization of those models, but actually those models, they do exist in your computer program. Okay, so actually this will also be discussed in this program. So actually by matter, I mean all three things. Okay, but actually, of course, you ask someone else, they may give you different. Say again. Sorry.
Quantum matter is made by quantum computers.
Not necessarily. Actually, so I would say quantum computer is a quantum matter. So for example, actually, what they use in Google, the quantum simulator, that is a quantum matter. So maybe I should say that a quantum simulator is one of them. Okay, so it's a quantum computer is itself a quantum matter. It can be used to simulate quantum matter, but itself is a quantum matter. That's why it can simulate quantum matters. Yeah. Anyway, so this is matter. Okay. So what about quantum? Okay, quantum. So for quantum, actually, certainly for all quantum mechanics, we have like a Hamiltonian, and actually in our, we have some restriction to what kind of Hamiltonian we discuss. Okay, so Hamiltonian, in our context, Hamiltonian actually is written as some local patch, some actually a Hamiltonian defined on a local patch of a lattice. Okay, local patch of the lattice. And actually, normally we discuss a local Hamiltonian, meaning that this part of the Hamiltonian only involves sites locally on the lattice. But later in the program, we will also discuss a completely non-local models like a SYK model, probably. So that's a very, very non-local model. But most of the time in the program, we will talk about local Hamiltonians. Okay, local Hamiltonians. And we will mostly be interested in the ground state of the Hamiltonian, mostly the ground state of the Hamiltonian. Okay, And actually, and also plus some low energy excitation. Okay, low energy excited state. Okay, low energy excited states. Okay, and actually by Gapless, okay, by Gapless I mean that suppose I make a plot, very rough plot of the energy spectrum of the Hamiltonian. There is a ground state. Okay, and then actually there's no gap to the first excited state. I mean that actually there's a lot of states here. Okay, a lot of states here. There's no gap. Okay, there's no gap. The reason we actually we want to study. Okay, the reason we want to study this kind of scenario is because actually normally a gap is related to the correlation length. Okay, there's a length scale. There's a characteristic length scale of the system, and this length scale usually is actually 1 over some gap. Okay, sometimes actually usually it's going to be 1 over the gap, which means that actually when a gap is very small or actually infinitely small. Okay, when the gap is vanishing, it means the length scale is actually very long. Okay, it means that when delta is actually small, it means that the correlation length is big. By big, I mean that it's much bigger than the lattice constant. Okay, the lattice constant. Okay, so we say this is my lattice constant. Okay, it's much bigger than lattice constant. Okay, and sometimes actually when delta equals 0, then Z actually over A goes to infinity. Okay, goes to infinity. And then this is the scenario where actually there's a lot of universal physics can happen in a system. Okay, universal physics can happen in a system. So universal physics usually is captured by some kind of renormalization group flow. Okay, it means that suppose this is my parameter space. Okay, whatever parameter it is. There's a G1 is one parameter, G2 is another parameter. Okay, so actually maybe at the microscopic level, my system is at some random random point of the parameter space. But actually, under renormalization group, they all flow to some fixed point. Okay, they all flow to some fixed point. Okay, all flow to some fixed point. So that means actually, in this kind of situation, when the C is much greater than A, okay, or when C is infinite, okay, the most ideal situation, then in this case, it doesn't really matter where we start on the parameter space. It means it doesn't really matter what is the details of the Hamiltonian. Okay, what's the details of the Hamiltonian? Okay, because eventually in the IR limit, if we only look at the long distance physics, long distance means that I look at physics at length scale far greater than A. Okay, far greater than A. Then actually the physics should be controlled by this point. Okay, some fixed point. Okay, so this is why I use the title legitimate spherical chicken. Okay, because actually a spherical chicken or sometimes spherical cow, okay, it's a joke that people mock physicists. Okay, people say that if I give you a chicken, you only know how to study it as a spherical chicken in vacuum. I'm trying to say that actually for quantum gapless system, it's perfectly okay to study it as a spherical chicken. Okay, because the non-spherical part, they are irrelevant. Okay, they're irrelevant in the RG sense. They are irrelevant. Okay, so we can just approximate all the different choices of the UV or microscopic parameters as some fixed point. Okay, it's perfectly okay to do that. Okay, but it depends on what questions we are asking. Suppose we are asking question about the distance way bigger than lattice constant, then it's perfectly okay to actually use the spherical chicken. It's perfectly okay to assume the system is actually at the fixed point or very close to the fixed point. Okay, so we can ignore a lot of details. Okay, a lot of details. Okay, so other than the universality, okay, so what else can happen around the fixed point? Okay, what else can happen around the fixed point? Okay, so I cannot use that all. Okay. Okay, so in condensed matter system, basically the UV physics or the microscopic physics, okay, microscopic physics, most of the time we are talking about electron. Okay, we're talking about electron. And the symmetry for electron is actually simple, and you can say it's boring, okay? There's a U1 symmetry associated with the electric charge. Okay, there's a SU2 symmetry associated with a spin. And sometimes there's a time reversal symmetry. Okay, time reversal. Okay, and actually there's a bunch of lattice translation symmetry, rotation symmetry. So these are the symmetries at the UV scale. Okay, at the UV scale. However, sometimes actually suppose we go to the IR. Okay, close to some fixed point, a lot of weird things can happen. A lot of amazing things can happen. Okay, so for example, we can have emergent symmetry. Okay, emergent symmetry. So for example, sometimes actually the symmetry can be, the IR physics can be far bigger than this. Okay, IR physics can be far bigger than this. And actually, so one particular situation which has been discussed is that actually this U1 symmetry can get enlarged into something, I'm going to write it in a very loose way, become something U1 to the infinite. Okay, U1 infinite. It means that there's an infinite number of conserved particles. Okay, this is what happens at Fermi liquid. Okay, this happens at Fermi liquid. Okay, this is what happens in Fermi liquid. So basically, Fermi liquid is probably the first class people learn in condensed matter physics. Okay, Fermi liquid is not that different from Fermi gas. Okay, basically we have like a free Fermi Hamiltonian. This equals to k squared over 2m minus mu. Okay, so basically the ground state of the system is just that we fill all the electron states below this chemical potential mu. Okay, it means so it means that in a 2-dimension we are just going to have a Fermi surface. Okay, this is kx, and this is ky. Okay, actually we are just going to fill all the states inside the Fermi circle. Okay, fill all the states inside the Fermi circle. Okay, so this is very simple as a non-interacting Fermi C. But suppose I turn on some interaction. Okay, suppose I turn on some interaction. So Landau, okay, Landau observed and actually showed that actually, the effective theory describing a large class of interacting Fermi system is actually in the IR actually, so every patch of the Fermi surface has a U1 symmetry. Okay, every patch on the Fermi surface has a U1 symmetry. So that means suppose I create a particle here. If I create a particle here, it has a very, very long lifetime. Okay, has a very long lifetime. It does not get scattered into other patches. Okay, it does not get scattered into other patches. Or in other words, the lifetime for the particle scattered, the lifetime for the electron, or what we call a quasi-particle, the lifetime of the quasi-particle. Yeah, let me say 1/over lifetime. Okay, 1/over lifetime of a quasi-particle. It scales as a e minus mu squared plus maybe b t squared. Okay, scales like this. Okay, it means that suppose I create a particle very close to the Fermi surface. It's very, very long-lived. Okay, it does not really decay so much. So this actually implies that actually if I create a particle at every patch, so every patch will have a particle number conservation. Okay, we'll have particle number conservation. So it means that this actually means that n theta. Okay, this means that n theta at every theta is actually conserved. Okay, it's actually conserved. Okay. So this is the first example where the IR symmetry or low energy symmetry can be much bigger than the UV symmetry. Okay, can be much bigger than the UV symmetry. And actually, over the years, people have realized that at low energy, the emergent symmetry, there are all kinds of emergent symmetries. For example, we can have a Lorentz invariance. Okay, Lorentz invariance. At low energy. Okay, so even though at UV we only have translation symmetry and some discrete rotation symmetry, but in the IR we can have the Lorentz invariance. Okay, we have Lorentz invariance, and sometimes we also have SUSY. Okay, supersymmetry. Okay, we also have supersymmetry. Okay, so this can be shown that if you have like a boson and a Fermi interacting system. Okay, and actually we know that SUSY a fixed point exists. You can tune the system. You can tune the parameters slightly away from the SUSY fixed point. You can show that actually the system will flow back, okay, to the SUSY fixed point. So that means that actually in this sense, the supersymmetry can emerge in the IR, even though it's not there in the UV. Okay, this also has been started. Okay, and also we also have a higher form symmetry. Okay, higher form symmetry. Okay, as an emergent symmetry. Okay, as an emergent symmetry. Okay. Okay, so yeah, right. So basically, this is what can happen in the IR of the system, of the condensed matter system. And actually, so the higher form symmetry is particularly useful, particularly related to what is called topological order. Okay, topological order. Okay, so because actually, well, I mean, the topological order was viewed as a new states of matter beyond the Landau paradigm, because we know the Landau paradigm classifies states of matter as like spontaneous symmetry breaking phase and a disordered phase with no spontaneous symmetry breaking. So topological order was viewed as a completely new state of matter, which cannot be classified by Landau theory. But now, with the higher form symmetry, topological order can also be interpreted as the spontaneous breaking of the higher form symmetry. Okay, in many of the examples. Okay, in many of the examples. But topological order is gapped. Okay, it's actually gapped. Okay, so this will not be a focus of our program, but actually, well, I mean, it's hard to avoid topological order. Okay, so we still have some talks about topological order, even though it's not really really gapless. Okay, so let me maybe spend a bit more time about Fermi liquid, and actually the physical phenomena related to Fermi liquid. Okay, so Fermi liquid, so it's a metal. Okay, Fermi liquid is a metal. Okay. Okay, and it's also a very conventional metal. Okay, it's also a very conventional metal. Conventional metal means actually you know, so if you have a resistivity, okay, resistivity versus temperature, okay, so for the Fermi liquid, we know, it should be a scale like this, rho naught plus a T square, okay? This is the residual resistivity at 0 temperature, and this is the T square, and this T square has to do with this T square, okay? This T square has to do, I mean, they are not exactly the same, okay, because this is related to the momentum relaxation rate, and this is a single particle relaxation rate. They are not exactly the same, but they are related. Okay, they are related. So this is what you are supposed to see in the Fermi liquid or ordinary metal. Okay, or ordinary metal. Okay, so this is what Landau theory would actually predict. Okay, however, in condensed matter, we both love Landau and we also hate Landau. Okay, so everything we do, if we want to do something cool, you need to go beyond the Landau. Okay, we need to do non-Landau stuff. Okay, we need to study non-Landau metal. Okay, non-Landau metal. So what are the examples of non-Landau metal? And I apologize that our field is very, very bad at naming things. So this is what is called a strange metal. Okay, this word actually is very, very non-specific. Okay, but strange metal means something very specific. Okay, it means that actually the rho as a function of t is rho naught plus something linear with temperature. Okay, linear with temperature. Okay, this is called strange metal. So this actually was seen and actually very well seen in the cuprates, in a class of materials called cuprates. That's the material with a high temperature superconductivity. Okay. So basically, this is the temperature, and this is some density of the electron, and there's some antiferromagnetic order, there's some high temperature superconductor, and above here, as the optimal doping, okay, we have this kind of behavior above the superconducting dome, okay, above the superconducting dome. And this behavior is true for very, very large energy window, okay, very large energy window. So it means this T, I mean, this behavior is valid between T greater than Tc and smaller than, well, like up to 1,000 Kelvin, okay? Up to 1,000 Kelvin, 10 to 3 Kelvin, okay? 10 to 3 Kelvin, okay? And actually, suppose you can suppress the superconductor with a magnetic field, for example. If you kill the superconductor, you can see that this can actually go to 0 temperature as well, okay? Go to 0 temperature as well. Okay, so this actually is a mystery. Okay, this is a mystery. Okay, it's not so hard to get this behavior at very low temperature, It's also not so hard to get the behavior at a very high temperature, but it's very hard to get this behavior across this very large energy window or temperature window. Okay? If you want a big price, this is a challenge that you may want to solve. Okay? I don't know how to solve it, but this is a challenge you may want to solve to win some big prize. Question?
Were the cube breaks the first ones that showed this?
Yeah, I think it's the first one. Yeah, but after that, this has been seen in many materials like in the Moray material. This was also this was also seen. Although in the Moray material, the whole energy scale is much smaller than this. But still, it's seen in the Moray material, in the heavy fermion, in different material, in different systems. But it's most famous in the cuprates. Okay, the most famous in cuprates. Okay, so what caused this? Okay, what caused? Certainly, this is a highly debated thing. Okay, this is a highly debated thing. But actually, so what I want to point out is that actually the fact that actually this is a very good linear and gamma does not change at all over this kind of very big energy scale. Actually, it seems very unnatural for many possible mechanisms. For example, suppose this is a phonon-driven mechanism. Suppose phonon, the oscillation of the the oscillation of the atoms in the system. Suppose the phonon drive this, then we should see some drastic change of the behavior around the Debye temperature, which is the typical energy scale of the phonon. But that happens at a few hundred Kelvin. Okay, but this does not change at all at a few hundred Kelvin. So, so actually it suggests that this has something more complicated, something more intrinsic than a phonon-driven mechanism. Okay, but this remains as a mystery until today. Okay, so this is a strange metal. So let me also talk, spend a bit more time to talk about another notion of exotic metal. Okay, another notion of exotic metal. This is called bad metal. Okay. Okay, bad metal. As I said, we are very bad at naming things. Okay, very, very bad naming things. Okay. So, so basically what is the simplest picture of a metal, okay, or resistivity, or something like that. So basically, the simplest picture is that we have an electron, okay. It's accelerated by the electric field, and it's scattered with an impurity, continuous scatter with impurity, okay, something like that, okay. So for this picture to be valid, we should have a notion of a quasi-particle, okay. So what does quasi-particle mean? Quasi-particle means that actually between the two scatterings, okay, I should be able to well approximate the electron state as a wave package, okay, as a wave package, okay, is that right? And actually, in a metal, as I said, in a metal, okay, in a metal, typically the electron excitation will be excited at the Fermi surface. It means that actually the wave vector for an electron should be at the order of kf, okay, order at kf, right? So this actually means that actually, for an ordinary or the elementary theory for metal to work, okay, to apply elementary theory, of metal, okay, we need the L mean greater than 1 over Kf, okay? The L mean means the distance the electron traveled between two scatterings, okay? Make sense? Okay? So it means that actually electron can be well approximated by a wave package between two scatterings, okay? Between two scatterings, okay? So this is the condition when we can use some very elementary theories. Okay, so this basically is called dude theory. It's also the first theory we learned in the solid state physics course. Okay, okay. So let's also estimate what is the resistivity or conductivity. Okay, what is the so basically the conductivity, especially I want to emphasize 2 dimension. Okay, conductivity in 2 dimension can be written as E squared over H times Kf times L mean, okay, equals to this, okay? The reason I emphasize 2D is because in 2 spatial dimensions, okay, the conductivity and the resistivity they are dimensionless. Okay, they are dimensionless, meaning that it's a dimensionless number times E squared over H. Okay, E squared over H. But in 3 dimension, actually, or 1 dimension, it's not dimensionless anymore. Okay, that's why when we read the experimental paper, when they measure like the resistivity for 3-dimensional material, the unit will be ohm times some length scale. Okay, but in 2D, the unit for resistivity is always just ohm. Okay, always just ohm. There's no length scale associated with it. Okay, so that's why I'm emphasizing 2 dimension. Okay, so in 2-dimensional conductivity is always going to be the elementary theory will predict E squared over H times Kf L mean, and we know that actually L mean needs to be much, at least greater than 1 over Kf. Okay, at least greater than 1 over Kf. Okay, for this theory to make sense. Okay, so this gives a lower bound. Okay, this gives a lower bound for the conductivity, or give an upper bound for the resistivity. Okay, or give an upper bound for the resistivity. So this bound is called a mod Ilford-Regal limit. Okay, or MIR limit. Okay, it means that the resistivity should be smaller than some order 1 number times H over E squared. Okay, H over E squared. Okay. Yeah. So it means that suppose you observe a system whose resistivity is way bigger than H over E squared. Okay, then it's exotic. Okay, then it's exotic. Okay, it's non-trivial. Okay, we cannot describe it using a very simple theory. Okay, we cannot describe it using a very simple theory. Okay, it's beyond what's called a quasi-particle description. Okay, beyond the quasi-particle description. Okay, so let me give some example of why this is a useful limit. Okay, why it's a useful limit. So, for example, actually, again in 2 dimension. Okay, again in 2 dimension. Yeah. In 2 dimension, for electron system with just disorder, but no interaction, okay? With just disorder, with no interaction, it means that actually the Hamiltonian of the system is still just a single particle Hamiltonian, okay? Only involves like a C dagger, this kind of term, but no interaction, no full Fermi interaction term, okay? But actually we break translation symmetry, okay? There's no translation symmetry at all. So this kind of system has been studied for many decades, and I think it has been understood pretty well. Okay, and actually the behavior of this kind of system depend on the symmetry of the system. Okay, depending on the symmetry of the system. Okay, for certain symmetry, the system have different behavior. So, for example, for some symmetry, depending on the disorder strength. Okay, depending on disorder strength, there could be a order-disorder phase transition. Okay, order-disorder phase transition. Okay, if you increase the disorder strength at low disorder, the system becomes a metal. The metal means that there's a finite resistivity. Okay, and actually when the disorder strength is over some critical value, the system becomes insulator. Okay, it means that resistivity becomes infinite. Okay, becomes infinite. And actually, people have developed some very formal non-sigma model description for the system, and actually we can even treat the resistivity as a coupling constant for the non-sigma model. And because resistivity is a coupling constant in the model, it can flow under RG. Okay, it can flow under RG. So this kind of a system, actually, the RG will flow like this. Okay, will flow like this. Okay. And it means suppose I start with the UV, suppose the resistivity is here, it will flow to 0. It means it's a metal phase. And if I start from here, the system will become insulator. Okay, system will become insulator. And the critical point is precisely located at the order 1 number times H over E squared. Okay, H over E squared. This is precisely, so if you look at non-sigma model, okay, the critical point precisely is at the row, it's at order 1 times H over E squared. Okay, it means that actually, suppose you have this kind of disordered metal without any interaction, you gradually increase the disorder strength. Okay, you will see that, okay, so here the resistivity will increase a little by little. Okay, however, as long as the cross H over E squared, it will immediately become infinite. Okay, it will become infinite. Okay, it will become insulated. Okay, so this is what it means. Okay, this is what it means. So there's an upper bound for the resistivity of a metal. Okay, upper bound for resistivity of the metal. Okay. So this is example 1. Example 2, okay, example 2 is an interacting system. Okay, it's an interacting system. And actually, this example is actually not a, okay, so this is the metal to insulator phase transition. Okay, example 2 is actually more like a superconductor to insulator phase transition. Okay, superconductor insulator phase transition. Okay, so basically, people can make like a very, very thin film superconductors, okay, very thin film superconductor with some disorder, okay, with some disorder. And by changing the thickness of the thin film, you can drive a phase transition between superconductor and also insulator, okay, and also insulator, okay? So this is what happens, okay, this is what happens. So let me plot, let me plot the resistivity versus temperature, okay, versus temperature, okay? So for some system, for some thickness, okay, for some thickness, the system becomes a superconductor, which means actually the resistivity will go like this and drop, okay, to 0, okay? And for some thickness, the system is an insulator, meaning that actually with your low temperature, it will become that, okay, go to infinity, okay? Then at the critical point, at the critical thickness, it will go like this. It's pretty flat, okay, it's pretty flat, okay? And the critical resistivity, this flat line, is pretty much at h over 2e squared. Okay, h over 2e squared. The reason is 2e squared is because the Cooper, superconductor is a condensation Cooper pair. So charge carrier carry charge 2, not charge 1. So that means that suppose I want to set a criterion for bad metal, I should use, E star equals 2e, not just e. Okay, so yeah, this is what's seen in experiment. Okay, this is what's seen in experiment. Okay, so there you can continuously tune this this thickness of the thin film. Okay, this is what you see. Okay, so basically this means that actually well, looks like actually it's very difficult. Okay, it's very difficult for a metal. Okay, it's very difficult for a metal to have a resistivity which actually is beyond h over e squared. Okay, difficult for that to happen. Okay, although theoretically this MIR limit only says that when the resistivity is greater than h over e squared, some very simple description will fail. Okay, but the theory does not exclude the existence of bad metal. But in reality, bad metal is actually not so easy to find. Okay, it's not so easy to find. Okay, okay. But not so easy to find does not mean impossible to find. Okay, does not mean impossible to find. Remember that actually I mentioned a strange metal. Okay, I mentioned a strange metal. Okay, I mentioned a strange metal. So strange metal incorporates in the high temperature superconducting material. Okay, so the rho equals to rho naught plus some gamma t. Okay, it increases linearly with temperature. Okay, increase linearly with temperature. Because it increases linearly with temperature, okay, at some finite temperature, it will have to cross the MIR bound, okay? At some finite temperature, it will cross that. Okay, so that means that strange metal is also a bad metal at a very high temperature. Okay, it's also a bad metal at high temperature. So, but strange metal itself is already a mystery. So, what happens here is total mystery. Okay?
What's the picture you have this U1 to the infinity convergence?
Say again, sorry?
You have the U1 to the infinity convergence symmetry that you mentioned earlier.
Yeah. Oh, it's not here. I'm afraid that so that symmetry is not here. I mean, so that symmetry will definitely require translation symmetry. Because as I said, the reason there's a U1 infinity is because at every patch of the moment in space, the particle number is going to be conserved, and this certainly requires momentum being conserved. But this is a disorder-driven phase transition. The momentum is definitely not conserved. So actually, that doesn't apply here. Yeah, that doesn't apply here. Right? Yeah. Okay. So yeah. Okay. So this is a hard question. But suppose we change the question we ask. Okay. Suppose we change the question we ask. Okay. So the question now. Suppose I change the question to be: can we construct a bad metal? Okay, can we construct a bad metal? Okay, with a relatively reliable method. Okay, this actually is a much easier question. Okay, much easier question to answer. A question?
Yeah, even this for a good metal, remind me to because T squared for rho.
Say again? For good metal, it's the rho. Yeah, it's T squared.
So why does that not even apply that you also?
Oh no, at a high temperature, it does not go T square anymore. That T square is only for low temperature. Yeah, it's only for low temperature.
So you said that you get this linear resistivity at low and high temperatures. Could you say
again? Sorry.
You said it's easy to get this linear relation at
Yeah. So, for example, people have tried. Okay. See. So first of all, as I said, Fermi liquid will give you something like this, right? T squared. So the general question is like, can we get something not this, right? Can we get some power smaller than 2? This can be realized by coupling the electron to some kind of fluctuating bosonic modes. And the bosonic modes could be some quantum critical modes. So that can be done. But we know very well that for any field theory to make any reasonable prediction, we can only apply the field theory at a scale way below the UV cutoff of the field theory. And the quantum critical point usually has a very low UV cutoff. Certainly not as high as this. Certainly not as high as this. So that means that I can cook up a model to give you that actually the behavior is different from T squared at a very low temperature by coupling the ferment to the quantum critical mode. But this behavior will fail at a certain UV cutoff of the quantum critical point, which is way below this. Yeah. Right. So the difficulty, I think the most difficult part is to why this behaves so nicely, so straight, okay, across such a big temperature scale. Yeah. Yeah. Anyway, so I was trying a question.
You wrote that the maximum temperature was a couple thousand Kelvin. What fixes that maximum?
Oh, because above that temperature, actually, your system. Well, I mean, so every material will melt at a very high temperature, right? So it's hard to. Yeah. Right.
It holds up to.
Yeah, it holds up to temperature you can access. So it's.
You also said that it's easy to get the linear behavior at very high temperatures. Could you explain that?
Yeah. So, for example, at a very high temperature, the scattering rate, the scattering rate will be proportional to T. Will be proportional to T, and also scattering rate will be proportional to T. So, for example, if you calculate how many phonons will be excited by temperature, it's going to be proportional to T. Yeah. So.
Could you explain that from a field theoretic? Because in the beginning, at low temperatures, you said you have this field theory which is coupled to some critical point, and then from a field theoretic point of view, is it easy to understand why at high temperatures again you get the linear behavior?
That's not really a field theory anymore, I think. That's more like it's much simpler than field theory, but still involves some equations. So I prefer not write them down right now. But actually, it's not so hard to expect this. So for example, if you can by some very simple schematic problem, right? You can estimate how many phonons or how many excitation are excited at a certain temperature T. Right, at a high temperature, it always scales linear with T. So you can just do the Fermi, you can do the distribution, expand with a linear with 1 over T. You will get that. Yeah. So, right. Okay. So now, So I'm trying to switch gear to a different question. Okay. Answering a realistic question is very hard. So let me try to answer a different question. Can we construct a bad metal? Okay. Can we construct a bad metal? So bad metal, by definition, okay, it means that actually, it's actually we cannot use electron as the basis for our description. Okay, we cannot use electron anymore. Okay, we have to use something else as a basis for our description. Okay, so this rings a bell of duality. Okay, this rings a bell of duality. So for example, we know there's strong-weak duality. Okay, strong-weak duality. Okay, so if I choose the most natural basis, could be extremely strongly interacting and a very hard to describe system. But suppose I choose some dual degree freedom. That dual degree freedom can be weakly interacting. Okay, it's easier to describe using the dual degree freedom. Okay, so the strong-weak duality is actually hard to easy duality. Okay, and actually in this particular case, could be the bad metal to a good metal duality. Okay, it could be the bad metal to good metal duality. Okay, so that means that actually the bad metal for electron, which is what we want to get. Okay, more accurately, a bad metal for charge is what we want to get. We just need to make a duality and see a bad metal for charge is a good metal for something else, and we just need to describe a system without something else. Okay, without something else. So it turns out that the bad metal.
Is your whole description very dimension dependent? Is it for two-dimension or?
Well, actually here, this MLR limit, they just use the resistivity divided by the thickness of the system. So actually they yeah, right. So they need to calculate or they need to actually evaluate what is the resistivity per layer of the system.
But the duality would change, right?
Yes, right, yeah. So this actually is a dimension sensitive. So I'm describing 2D right now. Yeah, dimension 2 now. Yeah, because so actually most condensed matter systems which actually are most interesting are 2-dimension. I don't know why, but it's the case. Yeah. Anyway, so turns out that a bad metal of charge actually is a good metal sometimes. Okay, it's a good metal of vortex. Okay, it's a good metal of vortex. Okay, so let me try to remind you what is a vortex. Okay, what is a vortex? Okay, so there's a famous particle vortex duality. Okay, particle or boson vortex duality. Okay, particle vortex duality or boson vortex duality. It means that actually, so for example, suppose this is the current of the charge. Okay, current of the charge. I can actually, I can write it as a gauge field. Okay, so this actually automatically satisfies the conservation law of the current. Okay, and then the charge of this gauge field is the vortex. Okay, because the gauge field can couple on charge, so the matter of the gauge field is the vortex. Okay, or more heuristically, let's think about what is a vortex. Okay, vortex is here. Okay, vortex is a local defect. And then the phase of the charge will have some kind of winding, okay, okay, around the charge, okay, winding around charge. So this is the phase angle, or the current, okay, or the current will have some kind of winding around the vortex. So suppose I rotate the current by 90 degrees, okay, I use a different color, okay, if I rotate the current by 90 degrees, okay, you can see that the vortex is just like a charged particle with an electric field line coming out of it. Okay, coming out of it. Okay, turns out this is exactly right. Okay, turns out this is exactly right. Okay, so vortex can always be viewed as a particle coupled to a gauge field. Okay, so these are the electric field of the gauge field. Okay, the vortex can also, always be viewed as a see, suppose I just want to describe a vortex. Usually it's hard. Okay, usually it's hard because the vortex is a massive thing. Okay, it's a very big object. But actually, if I view vortex as a charged particle coupled with some dynamical gauge field, okay, the description can be much easier. Okay, can be much easier. Okay, so this duality was actually exploited a lot in the condensed matter community. Okay, so for example, back in the early 90s, I think our colleague Matthew Fisher and Donghai Li, they run the duality and they made some identification. For example, well, the insulator of vortex actually physically is the superconductor of charge. Okay, superconductor of charge. Okay, also the superconductor of vortex, or we can say the condensation of the vortex, equals to the insulator of charge. Okay, equals to insulator of charge. Okay, so this was actually derived back in the early 90s. Okay, well, turns out that actually you can also derive another relation, which is that actually you can it's not so easy, it's not so hard to prove that the conductivity of the electric charge times the conductivity of the vortex is relatively a constant. Okay, it's relatively constant. Okay, you can pretty much prove that. Okay, you can pretty much prove. I mean, through a few lines of field theory derivation, you can kind of prove that. Okay, so this matches very well with these two lines here. Okay, so the insulator vortex means that this guy is 0. Okay, it means that because the product has to be constant, it means that sigma charge has to be infinite. That's superconductive charge. Okay, and suppose sigma v is infinite, which means that vortex is going to be a superconductor. It corresponds to charge being an insulator, has to be 0. Okay, so actually the match is this. I see a question. Yeah, that's a very good question. Yes, they say, yeah, right. So I will get to that maybe later. Okay. So first of all, yeah. How much time do I have left actually? Yeah, I will. Yeah. Okay. Yeah, I will try to wrap up. Okay. So this is consistent with these two equations, but actually, you can see that suppose I want to get a bad metal. It means that I want to get a metal where this guy is very, very small. Now I just need to get a vortex with sigma v very, very big. Okay, this actually is doable. Okay, this actually is doable. So for example, for the simplest setup, if I have like n flavors of vortex, okay, you have n flavors of vortex. Okay, you can imagine that I have n component of this thing. Okay, n component of this thing. They form a parallel circuit. Okay, they form parallel circuits. So that means actually the sigma v will be proportional to n. Okay, the parallel circuit. Okay, the conductivity of the vortex will be proportional to n species of the vortex. Okay, then this means that actually, a sigma v, sigma e, the electric charge conductivity, will be just proportional to 1 over n. Okay, times e squared over h actually. Okay. It means that the rho will be h over e squared times n. Okay, h over e squared times n. Okay. Okay. So now you can wonder, okay, how do I get many components of a vortex? Okay, how do I get many components of vortex? So it turns out that actually we can view the vortex as a particle. Okay, as a particle, and actually so the vortex. Suppose actually I have a momentum space. Okay, this is my momentum space for the vortex. Okay, the minima of the dispersion relation of the vortex may not be at a 0 momentum. Sometimes could be here. Okay, and then because of the lattice symmetry, once you have a minimum here, you have to have a minimum here, 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 here. Okay. So in some situation, the lattice symmetry can guarantee that you have a multiple component of the vortex. Okay, multiple component of the vortex. So in this scenario, actually, you can actually construct a bad metal. Okay, it's enhanced by a factor of n. This n comes, n is the number of vortex components in your system. Okay. Okay, then actually you can think, okay, why stop here? Okay, why stop here? Okay, so actually we can construct some even worse metal, okay, by making the vortex an even better metal, okay, make the vortex even better metal, okay. So how do we make a vortex even better metal? Okay, we need 2 steps. Step 1, make vortex a fermion, okay, that's right. And step 2, make the fermionic vortex a Fermi liquid. Okay, it's all right. Okay, because for the Fermi liquid, okay, the conductivity can be as large as you want. Okay, as I said, the sigma v is going to be kf, this kfv, okay, times L mean. Okay, kfv times this kf mean is kfv is the Fermi wave vector for the vortex, for the fermionic vortex. Okay, for the fermionic vortex. Okay. And as long as I keep the system very clean, which means that I make the disorder, the impurity distance very, very large, I can make the vortex a very good metal. Okay, I can make the vortex very good metal. So in this sense, I can make the charge conductivity proportion to the the vortex. Sorry, the charge resistivity proportion to the vortex conductivity times E squared over H. Okay, so it means that in this kind of particular system, the cleaner the system is, okay, the more insulating the system is. Okay, sounds very counterintuitive, but this is the consequence. Okay, this is the consequence by using the dual variable. Okay, the more clean the system is, it means that the longer the mean free path is. Okay, the vortex conductivity will be big, and then based on that equation over there, then the charge resistivity will also be very big. Okay, will also be very big. Okay, this all sounds very exotic. Okay, this all sounds very exotic, but actually it's realistic. Okay, this is precisely what happens at nu equals to 1/2. Lowest Landau level. You put electron in a magnetic field and make it very clean and make sure that you have filled the Landau level. Okay, this is a composite Fermi liquid. Okay, it's called composite Fermi liquid. Okay, composite Fermi liquid. Okay, so yeah, so this actually is a realistic thing. Of course, in the real Landau level, the story is slightly more complicated than this because there's a transverse transport. Okay, so this equation only write down the longitudinal transport, but actually in the Hall effect, there's a transverse transport. But actually nowadays, I think in Moray system, we can engineer some structure which actually to cancel out the transverse transport, so we can just see this. Okay, so we can just see this. Yeah, we can just see this as a bad metal. Okay, so let me say one more sentence about the thermal conductivity because there was a question out there. So, so for systems where we can use quasi-particle description. Okay, for systems where we can use the single particle description, you can imagine that the thermal conductivity is somehow proportional to electric conductivity because actually what carries charge also carries heat. Okay, electron carries charge. Electron also carries heat. Okay, so it means there's a relation between the thermal conductivity and the charge conductivity. Okay, so this is called Wiedemann-Franz law. Okay, it's called Wiedemann-Franz law. Yeah, so it means that the thermal conductivity for ordinary metal, it will be some constant times the T times the charge conductivity. Okay, times the charge conductivity. Okay, but actually, in this kind of bad metal, you can clearly see that okay, this relation has to be break. I mean, has to break, right? Because actually, what carries charge is not what carries the heat. Okay, so what carries heat is these vortices. Okay, the vortex actually they are the most dynamical thing in the system. Okay, the vortex form a Fermi surface. That's a lot of degree freedom. Okay, so the vortex will carry heat but does not carry charge. So what carries charge? Turns out the gauge field. Okay, the vortex will couple to the gauge field. The gauge field will carry charge. Okay, gauge field itself will carry charge. So in this kind of bad metal, turns out we have some very exotic modified composite Fermi liquid, which is something like this, okay, proportion to the electric resistivity rather than the conductivity. Okay, it's a very simple generalization. Okay, very simple generalization. Okay, so basically we expect bad metal to always have some very exotic behavior here. Okay, well, I have another whole section about the quantum critical point, but I don't think I have time to cover that. Okay, so I will stop here.
So I would expect that thermal transport is related to the stress tensor in the system?
Yeah, right.
Whereas charge transport is the current?
Yes.
Very often in systems there's some kind of Sugawa-like relation between the stress tensor and the current.
What relation?
Often some sort of Sugawa relation between. Well, let's say there's a component of the stress tensor that I can build out of current.
I know, but
so is this some statement that there's more to the system?
Yeah, I think so. When there are a lot of neutral degree freedom, it certainly contributes to the stress tensor. Yes, right. The vortex is the neutral degree freedom. Right. So the vortex is neutral, but it carries a lot of heat. So it contributes to the stress tensor, but does not contribute to the current.
Very
Say again?
What controls the statistics of the vortex?
Statistics? Oh yeah, there's something called a flux attachment. It's like or maybe so yeah. Since you're from string theory, right? So the transaminant theory. Okay, so basically there's a flux attachment can be described as transaminant theory, and the transaminant theory can turn the boson into fermion. So that's what's going on here. Yeah.
This vortex particle duality is often discussed in terms of theory, as we have already discussed. But at some point, you told us the difficulty of understanding this band metal because coupling, critical mode, and so on has a UV cutoff, and you cannot go beyond the UV cutoff temperature.
Yeah.
But according to your explanation, this vortex particle duality is valid beyond.
Yeah. So here I'm definitely not trying to address the cuprates problem.
Oh.
This is a completely different, much simpler problem. So I'm just trying to construct a bad metal at a 0 temperature. So I call it a quantum bad metal because it's 0 temperature. And actually suppose you try to compute or evaluate the resistivity of the system versus temperature. For the bad metal I was trying to construct, it will go like this at a low temperature. It will go down. Yeah, it will go down. So this point will be way above, way beyond h over e squared, but it will go down with temperature. Yeah. So yeah, by no means I'm trying to claim the big apple there. I mean it's very difficult. So I'm just trying to ask a simpler question, simpler and a controlled question that we can study.
Can you tell us if your punchline, if your last hunch that there should be a lower neutral degrees of freedom and they could show up at thermal conductivity,
Yes.
if that thing holds up for the response?
See, holds up.
If that thing is confirmed by experiments with the cuprates?
Oh no. Yeah, so this is not for cuprates. So this is a game which I'm trying to. Well, this is a game which I think may have to do with the Moray system, but not for cuprates.
So the thermal conductivity for the cuprates doesn't show it?
No, it does not. Sorry. Yeah, right. As I said, cuprates is a hard problem, and I'm not trying to solve that. I'm just trying to propose something interesting which may be seen in Moray system, 2D Moray system in near future. So.